Well, let's continue. So at the previous lesson we stopped when we have proved that if we have a short exact sequence and right exact functor f, then introduce long exact sequence of left-derived functors and if some functors ti from mod A to mod S satisfy these properties, namely if T0 equals F, Ti of P is 0 for P projective, and for any short exact sequence ABC, we obtain a long exact sequence FC, FB, FA, T1, C, and so on. And this construction is factorial in the sense that if we have two exact sequences and morphism between them, then we get a morphism between long exact sequences. Then the functors Ti coincide with the functors with left-derived functors of F. So in fact, in this way we can define left exact functors like functors that induce these long exact sequences when we have short exact sequence, but in this way we wouldn't know if they exist or no, and so we have defined in another way that guarantee that they exist. Now one more detail definition. Let we again have right exact functor f, then object module T, for example. T is called f acyclic if L I f of T is 0 for positive I, for I more equal to 1. So what we can say now is that one can compute left exact functors not only using projective resolutions but using f acyclic resolutions. Namely, if you have f acyclic resolution of some modulo x, F acyclic resolution means that the same thing as projective resolution, but the condition that members are projective is changed by the condition that they are F acyclic. So in particular, projective resolution is F acyclic resolution because you always have LIF of P is 0 for I more equal to 1 and P projective. So if this is F acyclic resolution of X, then Ln f x is isomorphic to H and T. So how to prove this? Let us take the beginning of this resolution. We have x t0 and some kernel, and it is a short exact sequence. Now we can apply our functor f and obtain a long exact sequence of x t0 x here 1 f x. Now here we have L1 f t0, but t0 is f acyclic by our assumption. So here we have 0, then we have L2 f kx, L1 f L1 f kx, L2 f x, 0, and so on. From these parts of long exact sequence, we obtain that L I plus 1 fx is isomorphic to L I f kx for I more equal to 1. So if we will show that L1 f can be calculated using f acyclic resolution, then we are done because for any module, then we are done because this this fact for kx and L1 implies this fact for x and L2 and so on. Then for any x we obtain L2, then L3 and so on. So it remains to understand that this one is exactly the first homology of T, and it is obtained in the same way as before, because T1, T0, x, here you have kx, and after application of f, you have f. Here you don't have injectivity anymore, and you obtain something which, as before, will be h1t. It is a general fact that if you have some, I told about this, but I don't remember at seminar or at lecture, that if you have like x, y, z, and you want to compute the homology, you can take here the kernel, here the image, and take the co-kernel of this. Or you can take here the co-kernel, here the image, and take the kernel of this. Of course. And the kernel of this map is of course the same thing as the kernel of the composition, because image lies in that. This one is monomorphism. So now we will look at one more construction. Now let we have two complexes. That would be x and y, I think. Okay, let it be u and v. U and v are two complexes. And f from u dot to v dot is a morphism of complexes. The cone of f is the complex I think it is u shifted by 1 plus v with differential yes, the cone of f. One second. So 0. I think here -1 in my notation. Like if you have u1 of -1 is 0. Yes. In differential, the u let us write this way. F dv. I will explain in more details what does this mean. This complex is denoted by conf f. So let us write down this complex, like some part of it. Let it be v0. So u shifted by -1 means that in the 0 degree you have what? You have u -1, yes? Like u shifted by -1, 0 is by definition u 0 -1. Yes, -1. So here you have this. Then you have u0 plus v1, u1 plus v2, and so on. Here you have u -2 plus v -1, and so on. And what's the differential? The differential is the following. You can write as a matrix, yes. Here you put du shifted by -1. It's the same thing as d minus du, yes, because we have defined the differential of the shifted complex with multiplication by sign. So here f, yes, and here dv. In this way, if you have some uv here, it goes to what? It goes to minus du plus sorry, minus du of u, and there it is f of u plus dv of v. Yes. And the fact that is interesting for us about the cone of morphism of complexes is the following. Let there be a morphism of complexes. Then f is a quasi-isomorphism and I forgot to say that quasi-isomorphism we always will write quiz if and only if cone f is acyclic. In fact, it can be deduced from a long exact sequence of short exact sequence of complexes, because it's not a proof for us. In fact, it's proof like if you look at this complex, then you will see that V is a subcomplex of it. Yes. Yes. So you have V, you have cone of f, and it's like a remark. And you have here u shifted by -1. And it is a short exact sequence of complexes in the sense that in each degree it is a short exact sequence. And these two maps are maps of complexes. You can check this. And then it induces a long exact sequence in homology. Of homologies. Of these complexes. And from this sequence you can deduce this lemma, but to do this you like to prove that there is exact sequence is not very difficult. You can have to apply snake lemma 2 times, but then you will have to understand what is the connecting homomorphism with this long exact sequence, because it has to be f to deduce exactly this. Yes, because what is here that the map on homology induced by f is isomorphism if and only if the homology of cone is 0. And you will have to show that the connecting map between homology is exactly the map induced by f. So it's a little technical. Our proof will be technical too, but at this moment it's easier to prove it, this fact. Yeah. So in fact, the canonical proof is using this long exact sequence. So let us look at the differential, yes, of this complex. It is du minus du 0f dv. I haven't checked this. It is a complex. Let us check this. Not have doubts. Like if you multiply, you will have what? You will have du square 0 here minus f du plus dvf, here dv square, and this one is 0 because du is a differential, this one is 0 because dv is a differential, and this one is 0 because f is a map of complexes. So it's 0, so everything is okay. Yes, now let us go to the proof. What does mean that cone of f is acyclic? Let us write this. This means that the kernel of this map coincides with the image of this map. So I'll just take some uv from here. So in fact, v is from some vi, u is from some u I minus 1, yes. And what does mean that it lies in the kernel of this map? It means that, first of all, du of u is equal to 0, and what also? F of u plus dv of v is equal to 0. Yes. This exactly means that uv lies in the kernel. And what does mean that cone of f is acyclic? This means that these equalities imply that uv lies in the image of this map. So there exists a pair u prime v prime. In fact, u prime is from ui, v prime is from vi plus 1. Yes, such that u equals to minus du of u prime, and v equals to f of u prime plus dv of v prime. So here we have written the condition that means the acyclicity of cone of f. Let's now write down the condition that f is a quasi-isomorphism. This condition splits into two conditions, of course. One of them means that f is mono, another one that f is epi. So f is mono, not f, h star f is mono. What does this mean? This means that if you have u from, for example, ui minus 1, such that du of u is 0, this means that u represents some element of in homology, and f of u equals to dv of v for some v. Yes, so du of u equals 0 means that u represents some element in homology. F of u is the element that represents some element in homology of v, and the fact that h star of f of u is 0 means that f of u lies in the image of dv, so it equals to dv of v, some v. Then u has to be 0, so u equals to du of u prime for some u prime. Yes. So here v is from vi. Here prime is from ui. And another condition is the surjectivity. That means that if dv of v equals to 0 from vi, yes. What does this mean? That v represents some element in homology. So it has to be an image of some element from u. So in this case, there are u prime from ui, such that f of v minus f of u prime lies in the is 0 in homology, so it is equal to dv of v prime. So this is also v prime from v plus 1. Two conditions, yes. So it remains to understand that these two conditions are equivalent to the condition on the left. Yes. So I think it's not very difficult, yes. We can leave it an exercise. Like from here it's easy to deduce these two conditions, and from here to there it's probably a little more difficult, but not very difficult, because you have here du of u equals to 0, so you can choose u prime such that u equals to du of u prime, and u first makes u 0 here, yes, and then you come to this condition. So you first take some u prime such that you subtract the image of u prime 0 from uv and obtain some 0 v tilde that is in the kernel, that is still in the kernel, and so you obtain some pair that satisfies this, but with u0, and this means exactly that dv of v tilde is 0, and you apply this condition and it will be done. So it's exercise. Okay, now let us go to the part that I have already started at the seminars. Let us go to the functor Tor. Functor. The definition is quite easy. Let you have, for example, A and B. A is right module, B is left module, both of them over R. Then Tor Rn of AB is by definition the left-right functor of the tensor product over R by B applied to A. So, the first problem that arise here is that we can define also, consider also the derived functor of the tensor product by A, yes, and apply it to B. And the question is if the same, is this the same thing? And it is the same thing. It's the symmetricity of the functor Tor. And we'll prove it now, I think. But before proving, we will introduce one more construction. Let us suppose that we have two complexes. U is a complex of right modules and V is a complex of left modules. Then we can construct the tensor product of these complexes. It's called tensor product complex. So it is a complex of like if there are no other structures on U and V, and we don't assume that I is commutative, for example, then it is simply a complex of abelian group, of course, because R is the right structure of V and the left structure of U. If R commutative, then there is a R module structure here, but it is because if R is commutative, then right module automatically becomes bimodule. So, in fact, when you have a module structure over commutative ring, you have at the same time right and left structure. You can, well, sometimes you can consider different right and left structures, but usually if there is no left structure, then it is the same as right structure in this case. And so more structures on tensor product arise. So to define the complex, we have to define its members, so in each degree and differential, and the nth degree of this complex is simply the direct sum for or I and j such that I plus j is equal to n, u I tensor v j. Yes. And the differential is the following. If you have some element here, it's enough to define the differential elements of this kind, yes. So if you have u tensor v from ui tensor vj, then d u tensor v of u tensor v is equal to du of u tensor v plus minus 1 in the ith power u tensor dv V. So this guy lies in ui plus 1 tensor V. This guy lies in ui tensor V I plus 1. And you can check that it's really a differential. But sometimes people construct right here. Sometimes people construct the tensor product complex in 2 steps. First of them, they construct double complex. Double complex is the following thing. Double complex is, for example, x. Yes, it is a. It is well, in terms of modules, it's a bigraded module with 2 commuting differentials of degree -1. But if you want to draw it, it's like this. You have elements xij. So here xi minus 1j, xi minus 2j, and so on. Here xi plus 1j, here x plus 2j, and so on. So here you have the numeration like in complex on each row, and on column 2 you have numeration like complex but using the second index. So here xi j plus 1, xi j plus 2, here xi plus 1 j plus 1, here xi minus 1 j plus 1, here xi plus 1 j minus 1, here xi j minus 1, xi minus 1 j minus 1, and so on. I write here one more, ij minus 2. But I think that it's clear how it works. And you have 2 differentials, one horizontal and another vertical. So on each row you have a differential, and on each column. So here let's denote this by the xh, yes, horizontal dh xh I j plus 1, the dx h I minus 1 j plus 1. So here vertical, so it is d plus 1 j xv, here d ij xv, here d plus 1 j minus 1 xv, and what more we need. And here we will write here d. Let's write this on the other side. So here d I plus 1 j xv. Here d I plus 1 j minus 1 xv. And here we have d I j xh, yes. And the condition to be double complex means that rows are complexes, columns are complexes, and squares are commutative. So, for example, here you have the composition of these two is 0, di minus 1, j plus 1, h, di j plus 1, h equals 0. Vertical compositions are 0. For example, this one, di plus 1, j minus 1, xv, d plus 1, j xv 0. The conditions and the commutativity condition that d j xh d plus 1 j xv plus d j xv d j plus 1 xh is 0. It's anti-commutative condition. Well, that would be anti-commutativity condition for simplicity. Sometimes you can draw it with commutativity condition. Commutativity condition, of course, when you put equality here, but in this way we will have more problems during construction. It will be a bigraded module with anti-commuting differentials. In this way, it will be easier to construct what we need. So, if you have a double complex, then you can construct its total complex. So the total complex of x is before. Is the coupling with the following members and differential. Its nth degree is the direct sum of x ij for all I plus j such that that give n. And the differential is simply dxu plus dxv. Yes. So if you take element here and want to apply differential, you apply this differential, get element here, and this differential get element here, and this pair lies in the direct sum of these modules. And these conditions guarantee that you will get a complex, because if you take element here and you apply 2 times differential, first of all you go here and get 0 here by this condition, then you go here and get 0 by this condition, and another way that you will go in this way and in this way. And this condition guarantees that you get 0 here too. So if we put before equality here, we will have to correct some signs here. But if we put the sum equals 0, you simply write this. So, and what?
Can you repeat last? Because
well,
I think that this operation is not defined correctly, because if we change the two d's, we get something else, right? If we write dxv plus dxn and do it in other.
dxv plus what? It's h.
Yes, if you change the order, first we do vertical and then.
No, it's the sum. It means that you apply, you take element, you apply to it one differential, another differential, and takes the sum.
Okay.
So the sum lies in the direct sum. Like one differential, if you take an element from one degree, you get two elements in different degrees, but the pair lies in the direct sum. So now the tensor product complex can be constructed in two steps. First, you construct the tensor product double complex, where xij is ui tensor vj. Here, I plus 1 tensor j u minus 1 tensor j tensor j minus 1 tensor j plus 1. All tensors are our. And now you have here simply du tensor 1v and here I don't know exactly what do you have. Well, I would write that you have here 1 u tensor dv but like this tensor product of maps is a tensor product of maps between graded modules. So when you apply 1 u tensor dv to some u tensor v, you have to multiply the result by the sign. Like the sign is the product of signs of the map and of u because you interchange them. It is u tensor dv of v, as everybody expects, but you have to multiply by the sign of dv, which is 1, because dv changes the degree by 1. So multiply by the sign of u. And here, if you have ui, it is exactly I. In this sense, you have dv. If you want to apply it directly, like to interchange, don't put sign, you have to put here minus 1 in the ith power. But in fact, you don't need, because you always have to work with graded modules and maps between graded modules. It is more convenient. Well, so now using this construction, we will prove our probably main theorem for today, that torr functor is symmetric. Well, the theorem will not state this, but as a corollary we will obtain this theorem. Let we have two modules, one right, another left. module. Suppose now that we have a projective resolution of A as a right module, of course, and the projective resolution of B as left module. Then we can form tensor product complex, and theorem states that the homology of this tensor product complex is exactly Tor of A and B. Well, by definition, Tor R of A and B is the nth homology of the complex A tensor P tensor RB. It's right here. P0 tensor RB, P1 tensor RB. B, so on. On the other hand, if we consider the complex P tensor over R Q, then there is a map. Well, let's denote these maps in some way. Let this be mu, this epsilon, yes. There is a map 1p tensor epsilon from here to p tensor b. Yes, and it is a map of complexes. Well, one can check. This map, like on pi tensor qj, this map is simply 0 if j more than 0, yes, and it is p. Sorry for, let's take here u and v, this from pi, this from qj. 0 if j is more than 0, and it is simply u tensor epsilon of v if j is 0, yes. So we want to show that this map that one p tensor epsilon is a quasi-isomorphism. And we know that it is quasi-isomorphism if and only if the cone of this map is acyclic. So we want to show that cone of 1p tensor epsilon is acyclic. But what's the cone of this map? Like if you consider, for example, Q0, Q1, Q2, so on, and you consider the map epsilon, yes, the cone of epsilon is simply the complex B, Q0, Q1, Q2, and so on, yes? Here epsilon, here minus dq, minus dq, q, and so on. By definition. And here the same situation, like the cone of 1p tensor epsilon is the tensor product complex. P tensor cone of epsilon. Or so what do we know now? We know that first of all, both complexes are bounded on the right, yes, like from some point they are zero, cone of epsilon and p. And we also know that p is projective, and cone of epsilon is acyclic, because cone of epsilon is a cone of quasi-isomorphism, yes? Well, it's clear from here, because from the definition of projective resolution that this complex is acyclic, but also by definition of projective resolution, epsilon is a quasi-isomorphism, and we know that cone of quasi-isomorphism is acyclic. So we need to show that if we have an acyclic complex and multiply it, make the tensor product of it with a projective complex, we still have a cyclic complex. We will do this by induction, which is strange because like we will make induction on the length of P, but P can have infinite length, of course, so it's strange. But on the other hand, if you look at the result, yes, like the assertion that I told before is a little incorrect. I was talking about complexes bounded on the right, because these complexes are bounded on the right. So if you look at this complex, yes, what's this? It's like, let's denote this complex by x, yes. It is x0, p0 tensor x0, p0 tensor x1, p0 tensor x2, so on. Then p1 tensor x0, p1 tensor x1, p1 tensor x2, and so on. P2 tensor x0, p2 tensor x1, p2 tensor x2, so on. Yes, and here zeros. And here zeros. So when we make the total complex at some degree, we use only finite number of p's. Like here we use only p0, here only p0 and p1, here p0, p1 and p2, and so on. And if we are interested in the nth degree, the result will not change if we like take only a part of complex. So, for example, hn of p tensor x, yes, equals to hn of p, less or equal to n plus 1 tensor x, where p less or equal to n plus 1 is the following complex. It's simply p until the n plus 1th degree, and then zeros. Yes? I? Сейчас. Because I don't remember if p(n plus 1) affect the nth homology, but probably affect. But n plus 2, of course, doesn't have anything with it, because like nth and n plus 1th members depend only on this part of complex. Nth and minus 1th, n plus 1th, and you are interested only in these three members when you compute homology, nth homology, yes. So we can proceed by induction on P and prove that if we have a cyclic complex, now I think it's not important if it is bounded or not, like the fact that here zeros is not important, and prove that its tensor product with finite projective complex is exact. And we can do this by induction now. So let x be acyclic. Then, if p is p0, then p tensor x, like length p is 1. Then p tensor x is simply p0 tensor x. And it is acyclic because projective modules are flat and they preserve short exact sequences, so they preserve acyclicity. Sorry, at lectures I haven't defined what is flat. Since tensor product with projective module preserves short exact sequences. And hence acyclicity too. This fact that tensor projective model preserves short exact sequences can be proved first for free modules where it's obvious, and then you simply use the fact that projective module is direct summand of free module. So now we can proceed by induction, and so let suppose that we have proved for the case where p has length n, then we want to prove for the case where p has length n plus 1. Not n, let be m. Length of p is n plus 1. So it is p n plus 1, pm, so on, p0, yes. And in this case, we can use the fact that it is cone of the following map, of the complex that has pm plus 1 in the nth degree. And the complex that we can obtain cutting pm plus 1. Yes. And we again use the trick that cone. Let us denote this complex by, not denote, it's exactly p m plus 1 shifted by minus m. And this complex does denote by p bar, yes. Then cone of p tensor x is equal to cone, cone, and p tensor x is equal to cone of this map. So it's cone of some map from P m plus 1 shifted by minus m tensor x to P bar tensor or Rx. And this complex is acyclic by induction. And this complex is acyclic as before because Pm plus 1 is preserves short exact sequences. Since Pm plus 1 preserves cyclicity. Pm plus 1 tensor preserves cyclicity. So this complex is a cone of a map between two acyclic complexes, but a map between two acyclic complexes is of course quasi-isomorphism because any map between two zeros is isomorphism. So we are done. So we are done, and and as I told before, this means that homology of P tensor Q is isomorphic to the homology of P tensor B, which is exactly Tor Rn of AB. But in the same way, we can prove that they are isomorphic, that is isomorphic to Hn of A tensor over Rb. And so we get a corollary. Huh? Sorry, Q. That says that Ln of dash tensor Rb of A is isomorphic to Ln of A tensor R dash of B, and this guy is denoted Tor N R A B. And so we get that the Tor functor is symmetric in its arguments. Well, let's now give one definition. Yes. Let X be a module. Then X is called flat if the functor x tensor over R is exact. Since the tensor product functor is always exact, then this is equivalent to the fact that x tensor over R m x tensor over R n here 1x tensor f is mono if the map, the initial map from M to N is mono. So modulo is flat if and only if it preserves monomorphisms. If the tensor product with it preserves monomorphisms. So by our observation that we made before, Tor functor can be computed using flat resolutions. Projective modules, of course, flat. Sorry, I have used some fact that was proved in seminars, but it's not very difficult fact that a module is flat if and only if x is flat. Sorry, 1 minute. X is flat. If and only if x is tensor over R y acyclic for any left R module y. Well, it can be left as exercise, but we have done it. At seminars we have talked a little about flat modules. We know that, or we will know that for a big class of modules, flatness implies projectivity. On the other hand, we know that there are flat modules that are not projective. For example, Q over Z is flat but not projective. But this will follow from the fact that we are going to prove, and now we will start probably, while it will take some time. So definition. Let J be a small category. It is called filtered. If two conditions are satisfied. First one. If we have two objects, with the category J, then there exists a third object K such that home J of IK and home J of JK are not empty. So if you have two objects, I and J, then there exists K and two arrows from I to K and from J to K. And the second one is the following. If you have two objects I and J and two morphisms between them, and G are morphisms from I to J, then there exists some object K and a morphism from J to K. So we'll write in one formula. There exists H from J to K. So there exists K and H from J to K such that HF equals to HG. So if you have IJ, you have two morphisms, then you can take some K and this, such a way that this composition is equal to this composition. So you can equalize them. And in fact, where we will apply what we want to prove, we will not need the second conditional, because we always will apply it to direct limit that comes from the category of formed by submodules or subgroups of something, and there you have if you have an arrow, if you have two objects, then there is or 0 or 1 arrow between them. So we will not need the second property, and it's easier at this point probably to change it by the property that if you have two objects, then home between them is not more than one, has not more than one element. When we will come to some proof where we will need this, we will think about is it better to prove in this generality or to prove less general thing, because we don't need this. So what we are going to look at is filtered colimits. Filtered colimit is a colimit of a functor from filtered category to somewhere. In fact, to a category under consideration. We will consider, of course, filtered colimits in the module category. So our lecture time is finished.